Welcome back, ladies and gentlemen, to my course on the Introduction to Mathematics. In this lecture we are going to learn about proofs. To obtain new knowledge in mathematics we use logical reasoning. We begin with certain propositions that we assume or know to be true, and from these we form new true propositions according to the rules of logic. And the process of doing so is called a proof. In previous chapters we learned about logic and sets and how to use them to express mathematical statements. So in this video we will look at techniques to prove new propositions and some strategies to go about your proofs. It is important to realize that doing mathematics is not just proving stuff. The creative process also requires ideas about what new propositions are important to one's research and essentially to ask the right questions along the way to your end goal. Getting these ideas is a matter of experience and depth of understanding of the subject you're studying. It is hard to teach in a formalized manner, and you will pick it up by and by while doing mathematics. The Hungarian mathematician George Polya wrote a famous book called How to Solve It on strategies of problem solving, and I want to warmly recommend this book to you as it contains a lot of interesting examples of proofs and other problems solved with some detailed explanations on how the ideas for the solutions are developed. Here I just want to quickly show you Polya's 4 major points. The first one is to make sure you understand the problem. So look at the terminology that is used and make sure you understand all the terms that appear in the problem description. Understand what the assumptions are, and then understand what the desired outcome is. For example, what is the statement that you are expected to prove and how do its parts relate to the assumptions? The second step, once we fully understand what the task is to make a plan. First, what do the assumptions provide us with? Do we recognize any important properties of the stuff we have to work with? Can we find a connection to the desired result? Also, do either assumptions or the goal remind us of similar problems whose solutions could be helpful for our case? Could we solve the problem if we simplify it? Once we have a solution for an easier problem, we might be able to extend it to our original problem. The next step is simply to carry out the plan. So we diligently carry out the plan, carefully checking that we do not make mistakes and that we do not get tempted into taking shortcuts. That is very important. And once the problem is solved, we can look back and see what else this solution can give us. If we can derive the result in a different way, this might shed some additional light on the structure of the original problem. Or just like before the solution, we asked if some other problem might help us solve the one at hand, we could now ask if this problem, or its solution rather, can help us with other problems. We will more or less explicitly encounter these steps in the proofs throughout this course, and eventually we will use them without thinking too much about them when tackling new problems. But there is one problem that you can easily help me solve right now, and that is the infamous low subscriber count problem that affects many YouTubers. And all you need to do to solve this is to like this video and subscribe to my channel. Thank you very much. Now let's see what we will be doing in this video. First we will be looking at direct proofs where you are given some assumptions and then using logical techniques step by step move towards a claim that you want to prove. Then we look at proofs by contradiction and contraposition, where you actually use the negation of the claim you want to prove to show that this cannot be true, and thereby deduce that your original claim must be true. We will look at certain proof strategies, and finally we will look at the technique of proofs by induction. So we start with direct proofs. And in a direct proof, we employ implications, if necessary, multiple implications, to get from our assumptions to the claim we wish to prove. So here we begin with some assumption A, which we take to be true, and under this assumption we want to show that the claim B is true. And to do this, we actually prove the implication A implies B. Now, if A and A implies B are true, then B must be true. We can see this from the truth table for the implication. So if you recall that from the lecture on logic, this is the truth table, and we see if A is true, and if A implies B is true, then the only option is that B is also true. Often we have to use several intermediate steps to get from the assumption A to the claim B. So we first prove that A implies X, then we prove that X implies Y, and so on, blah, 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 until we arrive at some proposition Z that implies B. Let's look at an example for direct proofs. So consider the following two sets, X and Y. So X is the set of all numbers 2n plus 1, where n is an integer numbers. So in other words, X is just a set of odd integers. And Y is the set of all elements x squared, where little x is taken from the set big X. So in other words, Y is the set of all squares of odd integers. What we want to prove now is the following. If y, little y, is contained in the set big Y, then little y is also contained in the set big X. Or if we say this in words, the square of any odd integer is again an odd integer. Okay, let's recall Polya's approach to problem solving. First, understand the assumption that is made that little y is an element of this set Y here. This assumption means that Y is equal to x squared, as we write it here, for some element x in the set big X. Now, what does this mean? It means that the element x is some odd integer, so we can write it as 2 times n plus 1 for some integer n. And what does this problem here ask of us? We have to show that this square, y, or rather x squared, is again an element of x of this set here. So it's again an odd number, and that means we have to show that x squared is also of this form here, 2m plus 1 for some integer m, so which of course is probably going to be a different integer from the one that we used for x. And now our plan is to use the definition of y as the square of an odd number x, write out the odd number explicitly and compute the square, and hope that from this expression we somehow find that it turns out to be an odd number as well. So let's execute the plan. Y is the square of the odd number 2n plus 1, which was just our x. And if we expand this expression here, we get 4n squared plus 4n plus 1, which equals 2m plus 1, where we take m to be 2n squared plus 2n. You can verify this. If you plug in this for m here, you get exactly this expression. So what we found is that y is again of this form 2m plus 1, which means y is an odd number, which means that y is an element of the set X, and that is what we wanted to prove. So our proof is done, and I mark the end of the proof by this little box here, which is quite customary. Some people read this as QED, for the Latin quod erat demonstrandum, which is a common phrase to mark the end of your proof. Let's look at another example. Here we are given three integers d, x, and y. And we wish to prove that if d divides x and if d divides y, then d must also divide their sum x plus y. So again, let's make sure we understand the assumptions first. Here, d divides both x and y. And this means that there exists some integer number m, such that m times d equals x. And there exists some integer number n, such that n times d equals y. That is simply what dividing means. So what do we wish to show? We want to show that d divides x plus y, the sum of x and y. So this means there must exist some integer number k, such that d times k equals x plus y. And our plan is to use what we are given, namely that we can write x and y in this form, m times d and n times d, and plug this into the sum, and then hope that we can somehow see that d divides the sum. Let's do this. So we take x plus y, plug in these expressions here. So we have m times d for x and n times d for y. And then we can take out the d here, and we get m plus n in parentheses times d. Yeah, and then we're done. We see that d times this number here gives x plus y, which means nothing but d dividing x plus y. And again, we're done. This is what we wanted to prove. Now we look at a different method of proof. Instead of proving directly that some proposition B is true, we want to use the fact that B must be true if we can show that its negation, not B, is false. And this is proved by contraposition, and it makes sense if we reconsider the implication. So let's recall its truth table again for the implication A implies B. And we compare it to the following truth table. Not B implies not A, and we see that the truth tables are identical. So this means A implies B is equivalent to not B implies not A. And so instead of proving A implies B, we can just as well prove not B implies not A, which sometimes is actually easier. Let's look at an example. Again, we have an example involving odd numbers. So here we want to show for an integer n, if n square is odd, then n must be odd. Now note that this is the converse statement of our first example. In the first example we proved that if n is an odd integer, then its square is also odd, and here we go the other way. We assume the square is odd, and then the original number n must have been odd already. And trying to prove this directly turns out to be quite tricky, but the proof by contraposition is surprisingly easy. So we formulate the contrapositive of our problem. So we want to prove if n is even, then n square is even. Okay, so look what we did here. This is A implies B, and what we did, we negated both parts and reversed the order of the implication. So A implies B is equivalent to not B implies not A. Let's go about the proof. The assumption is now that n is even. So This means n is equal to 2m for some integer m. And what we want to show is that n square is also of the form 2k for some integer k. So let's compute. We take n square and plug in the even number 2m for n, so we get 2m square. We compute this to be 4m square, and yeah, this is in fact 2k, where k is the integer 2m square. So this means n square is even as well. And that was quite easy, wasn't it? And if you try to prove this directly, you will actually find it's a bit more complicated. So we should be glad we have the contraposition. Now it's your turn to do something. So pause the video for a few moments and show, similarly to the previous example, if n square is even, then n is even. Okay, so I hope you gave it a try. And did you notice that what we have to show here is essentially the same as we did in example 1? We use contraposition, which means if n is odd, then n square is odd. And in example 1 we formulated this with two sets, x and y, but the computation is exactly the same, but I will go through it once more. If n is odd, then n is of the form 2m plus 1 for some integer m. Now we square this expression here. 2m plus 1 squared is 4m squared plus 4m plus 1. We can take out the 2 and get 2 times 2m squared plus 2m in parentheses plus 1. So we have 2k plus 1, where k is just the expression in parentheses here. And this means n square is odd. A proof by contraposition is often formulated as a proof by contradiction. And here we wish to prove some claim B, but we assume that not B is true and derive a contradiction to our prerequisites from it. And in that case, B must necessarily be true. Okay, so we assume something, we assume A, want to prove claim B. What we do is we assume that B is false, and then we show that A must be false as well. So we use the contraposition. But since we made the assumption that A is true to begin with, we derive a contradiction, and that means B must be true. And as an example of a proof by contradiction, we want to prove that the square root of 2 is not a rational number. So in other words, the square root of 2 cannot be written as a fraction pq for some integers p and q. And if you like, you can think of this as the hello world of proofs, as it is one of the first examples of a non-trivial proof in every math course. Our approach is a proof by contradiction. So we assume the opposite of what we want to prove. We assume that the square root of 2 is in fact a rational number. So that means we can write square root of 2 as a fraction in this form. Then we want to derive a contradiction from this assumption, and this in turn means that our original claim must be true, being that square root of 2 is not a rational number. So by our assumption here, we have integer numbers p and q with the denominator q different from 0, such that square root of 2 is the fraction p over q. And now it's very important that we can reduce fractions, and we can assume that this fraction square root of 2 equals p and q is reduced. So we may assume that p and q have no common factors. For if they did, we could just cancel the common factors and replace p and q by these new values where we remove the common factors. Okay, so this is again an important assumption we make here. P and Q have no common factors. And to go on with the proof, we have to use what we are given, that is the square root of 2, and by squaring our assumed equation here, we can obtain an equation with integers only, which hopefully will be easier to manage. So we square this equation here, and it becomes 2 equals to p square over q square, or equivalently, if we multiply by this, we get 2q square equal to p square. Now, 2q square is an even number, hence p square is even. Okay, because p square is equal to this even number. But from the last exercise, we've just learned that if p square is even, then p must be even. So now we know that p is an even number. So p is equal to 2n for some integer n. And in particular, if we plug this in here again, we get 2q square equal p square equal 4n square. But now we can cancel 2 on both sides of this equation. So we cancel the factor 2 and we get q square equal to 2n square. But this means q square is an even number because there's a 2 here. And again, using the same argument from the last exercise now, this implies that q is even. So we found so far that p is an even number and q is an even number. So that means both p and q share a common factor 2. Now that's a bit of a problem because we assumed that they do not have common factors. We assumed we had a reduced fraction. So now we have a contradiction. And because of that contradiction, our original assumption that square root of 2 is a rational number cannot be true, and hence the negation must be true, that square root of 2 is not a rational number. And this concludes our non-trivial proof by contradiction about a rather interesting number theoretic statement. Next up, we look at strategies for how to approach proofs. And often there are many different ways to go about proving a proposition, and some approaches are easier and more efficient than others. So suppose we wish to prove an equivalence of two propositions, A equivalent to B. There are basically two ways to go about this. The first one is suited for easy cases, where you can simply follow a sequence of equivalences. A is equivalent to A1, equivalent to A2, until we get to some equivalence that is easily shown to be equivalent to B. So here we assume that each of these intermediate equivalences can be easily verified directly. But if such a sequence is not possible, then it may be easier to split the proof of the equivalence into two implications. So A equivalent to B is equivalent to A implies B and B implies A. So if we want to prove this, we can instead prove first that A implies B, and then we prove that B implies A. And if we've done that, then we've proved that the two statements are equivalent. I will give you an easy example for this, and we want to show the following equivalence for a natural number n. N is an even prime number if and only if n is equal to 2. So this statement seems pretty obvious and the proof is quite simple, but I will just use it to show you the principle of splitting the equivalence into two separate directions. So I split the proof in the directions from the left to the right. So here, for this direction, I will assume that n is an even prime number, and then I will conclude that it has to be 2. And for this direction, I will assume that n is equal to 2, and then conclude that it is an even prime number. And I will actually do this one first because it's really easy. Basically just write it down. So if I assume that n is equal to 2, then, well, obviously n is even. And it is a prime number since the number 2 is only divided by 2 and by 1. So this part is done. Now the opposite direction, I assume now that n is a prime number and it is even, and I want to show that n has to be 2. Now since n is an even number, I can write it as 2 times k for some natural number k. And this means n is divided by 1, by 2 and by k. But if we assume that k is anything but 1, then n has at least 3 distinct divisors, namely 1, 2 and 2k. And this contradicts n being a prime number. Because if n is prime, it can only be divided by 1 and by itself. And here we already have 3 distinct divisors if we assume that k is not 1. Now, you may ask, why do I not say 4 distinct divisors? Because k is also a divisor, but I could have the situation where k is equal to 2, then k would actually not be a distinct divisor, and but 2k, which would be 4 in this case, would still be a distinct divisor. But for any k other than 2, I would in fact have 4 distinct divisors here. Anyway, we have a contradiction to n being prime if we have anything but k equal to 1. So this means k must be 1, and therefore n is equal to 2k equal to 2, as we claimed. And this concludes this direction of the proof. Now we've shown both directions, and that means we've shown the equivalence of these two statements here. N is an even prime number is equivalent to saying n is equal to 2. And we can take the strategy of splitting the equivalences a step further if we have several propositions that we should prove to be equivalent. So for example, here we have A, B, C, and D, and we want to prove that all of them are equivalent to one another. And what we can do here is we can use this cyclic approach. We prove that A implies B, B implies C, C implies D, and then coming back to the beginning that D implies A. Now, if we use the split strategy from before, where we replace every equivalence by 2 implications, then this would amount to proving 6 implications, 2 between each 2 of the propositions here. So by using this cyclic pattern, we could actually reduce our work a little bit. However, it's not always possible to do this. Very often you can do it if you have multiple equivalences to follow such a cyclic approach, but in some cases it just may not work out easily that way. But it's always worth trying. And I'm not going to show you an example of this right now, but we will see many examples later on in the course. So look out for it. The next is a straightforward approach to test the truth of a proposition with a universal quantifier. So you have something like this here. We are given a set big X, and the claim is that for all elements of this set big X, the property P should hold. And suppose we want to prove that this claim here is not true, so we want to prove its negation. Then, if you recall from the logic video, the negation would be that there exists an element X in the set big X such that this property does not hold for this particular X. And this is what we call finding a counterexample. So it is enough to find one single counterexample, one single element X in the set big X that satisfies the negation of this property P, and then we would know that this here cannot be true, because it just can't be true for all x if we find one x that doesn't satisfy this. Here are two very simple examples. Test if the following statements are true. First, all swans are white. And second, for all natural numbers x, x is strictly smaller than 2x. Both are false, and we use counterexamples to show it. So the first one is false because if you've ever been to Australia, for example, you would have noticed that there are many, many black swans on this earth. So yeah, even multiple counterexamples are allowed. It doesn't have to be precisely one. In the second case, we actually have precisely one counterexample. So this is also false if we say it should hold for all natural numbers x, because if we take x equal to 0, then, well, 2 times 0 is still 0, so x equal 2x. But note that this counterexample only works because by our convention we include the number 0 in the natural numbers. Some authors do not do this. So some authors would take 1 as the smallest element of the natural numbers, and for those authors this statement would actually be true. Okay, so be careful with the definition of the natural numbers, and make sure wherever you read about it to understand whether the author uses 0 or 1 as the smallest element. Now pause the video for a moment and show that the following claim is not true. All prime numbers are odd numbers. So I hope you thought about this for a few seconds, and we can give a counterexample to this claim, which is the number 2. 2 is a prime number, but it is not odd. So it's a counterexample, and yeah, we just had this in example 5 before, and it is in fact the only counterexample to this claim. So every prime number other than 2 is odd, but we have one that is not odd, so this claim here cannot be true. Now we come to induction, a proof technique that is quite different in flavor from the previous ones. It is a technique specifically for statements on the natural numbers. Proofs by inductions are used to prove claims about the natural numbers or subsets of them. So for example, we could prove a claim that the sum of all natural numbers from 1 to n is equal to n times n plus 1 divided by 2. This is something we could do by induction or similar statements. And proofs by induction work because the principle of induction holds, and this one is stated as follows. So Pn is some predicate depending on a natural number n, and if the following hold, firstly, P is true for a certain initial value n0 in the natural numbers, and it is true that if P holds for a certain natural number n, then it also holds for the next natural number n plus 1. Then Pn is true for all natural numbers greater or equal to our initial value n0. And this is what the principle of induction states, and here we take it as an axiom. That is, we take it for granted that the principle of induction is true, and therefore proofs by induction work. And note that the principle can be formulated with a strong version, which appears to be a stricter criterion, where the second part is replaced by that P being true for the initial value, and all values between the initial value up to a certain value n imply that P is true for the value n plus 1. But in fact, this version here and this version here are equivalent. We do not show this here, but we can use either version equivalently in proofs by inductions. The strong version here is sometimes more convenient in proofs by inductions because we might have to refer to several smaller values during the proof. Induction is often compared to domino stones, where each stone will push over the next one if it falls, and once some initial stone, n0, falls, then all the other stones following it will fall. So the first part of the principle induction corresponds to one of the stones in our domino queue being pushed over to begin with, and the second part corresponds to that one stone falling will always cause the following one to fall. It's actually quite a good metaphor for induction. Now, proofs by induction work as follows. So we're given some predicate Pn, which we wish to prove for all n greater or equal to some initial case n0. Then what we have to do, we have to prove the initial case, we have to prove the claim P of n0 for this desired initial value n0. And then we formulate the so-called induction hypothesis, which I abbreviate IH here for short, which states that for some n greater or equal than our initial value n0, it is true that Pn holds. Or the equivalent strong version, for some n greater or equal the initial value n0, it is true that Pk holds for all numbers k from our initial value on up to some certain value n. And in this step there's nothing to prove. We're merely formulating an assumption that we will need and use in the next step, which is the induction step. So once the induction hypothesis has been made for a certain number n, we try to prove that the corresponding claim P holds for the next number n plus 1. So we assume it holds for n, or for all numbers up to n in the strong version, and then we want to, using this assumption, conclude that it also holds for n plus 1. And if we succeed in the last step, and of course in the initial step, then the principle of induction guarantees that Pn holds for all natural numbers n greater or equal to our initial value n0. So, a famous first example is the Gauss summation formula, which is the following. We take the natural numbers from 1 to n and we sum them up. 1 plus 2 plus 3 plus 4 blah 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 and so on up until n. And the result is this nice formula here. It's n times n plus 1 divided by 2. Note that this is always an integer because we have n and n plus 1. One of those two has to be an even number, so the numerator is a multiple of 2, so we can actually divide by 2 and get an integer number out. And according to legend, the 9-year-old Carl Friedrich Gauss was given the task to add all the numbers from 1 to 100 in school one day because his teacher wanted to have some peace and quiet from his pupils. But Gauss just wouldn't let him and solved the problem within a minute by cleverly arranging the numbers from 1 to 100 in pairs in the following manner. So he took 1, 2, 3, 99, 100, and then he wrote them in the reverse order, 100, 99, and so on, until 1. And he noticed that the sum of every pair yields 101. So adding all these 100 pairs yields 100 times 101. Now, of course, in this scheme here, every number appears twice, so what's left is to divide by 2, which yields the result. The numbers 1 plus 2 plus 3 blah, 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 plus 100 gives 100 times 101 divided by 2, which is 5050. And you see this is exactly this formula with n equal 100. And of course you could easily generalize this as a proof for arbitrary n. But we're here to learn induction, so this is a nice story, but it doesn't really help us with learning induction. So we'll prove the same result again by using an inductive proof. We start with the initial case and 0 equal to 1, which is easy to check. We have 1 equal to 1 times 1 plus 1 divided by 2, so we plug in 1 for n here, and this is 2 divided by 2, which is equal to 1. So the initial case is done. Now we formulate the induction hypothesis. Recall what I said, there's nothing to prove here, we just state that the desired result should be true for a certain number n greater or equal our initial case. So we assume now that 1 plus 2 plus up to a certain number n equals n times n plus 1 divided by 2. And now, having made this assumption here, we want to prove that the formula also follows for n plus 1. So I write this somewhat laxly here, n squiggly arrow to n plus 1, so this doesn't have a deeper meaning, it just means that I take the induction step, assuming the statement to be true for n and wanting to prove it for n plus 1. So we consider the sum of the numbers 1, 2, up to n plus 1, and we can use the induction hypothesis in the following way. So we write out the sum, and the first n summons in this sum are just what makes up the induction hypothesis here. So for the first n summons, I can use the induction hypothesis to substitute n times n plus 1 divided by 2, and I'm left with one additional summoned here. Now I can play around with this. I multiply this by 2 and divide it by 2, so I have the same denominator here, and what I get is n plus 2 times n plus 1 divided by 2, and if you check, this is exactly the desired formula, but with n replaced by n plus 2. So we found that the desired formula also holds for n plus 1. So we've completed the induction step successfully, and now the principle of induction tells us that the formula holds for all n greater our initial value 1. So it holds for all positive natural numbers. And as a second application, I want to state the first little theorem in our course. And by a theorem, I usually mean a very important proposition that is well worth remembering. And that is that every natural number n greater than 1 is a product of prime numbers. We prove this by induction. The initial case n0 is equal to 2. 2 itself is a prime number, as we have repeatedly stated today. So this case is true. We formulate the induction hypothesis for a certain natural number n greater or equal to 2. All numbers between 2 and this particular n, including 2 and n, are products of prime numbers. And now we make this assumption and want to prove that it holds for n plus 1. So if n plus 1 itself is a prime number, we have nothing to prove. Otherwise, if n plus 1 is not prime, it must be the product AB for some natural numbers that are greater or equal to 2. That's directly from the definition of not being prime. Moreover, because these two have to be multiplied to give n plus 1, they're both smaller than n plus 1, so the induction hypothesis applies to them, because all the numbers between n plus 1 and 2 are included in this range here. So by the induction hypothesis, we can write both a and b as products of prime numbers. So let's say a is equal to p1 up to pm, and b is equal to q1 up to qk, where all of the p's and q's are prime numbers. And it could be that some of the p's are actually identical, so that's not really excluded, but it doesn't matter. Well, and then we have n plus 1 equal a times b is the product of p1 to pm times q1 to qk. So we find that n plus 1 is also a product of prime numbers. And now the principle of induction tells us that all natural numbers greater than 1 are products of prime numbers. And it is important to note that this theorem can be made much stronger, namely that the factorization into prime numbers not only exists, but is in fact unique for every number n. And this was famously proved by Euclid in antiquity around 300 BC. It's a very important theorem in number theory, and here we have a rather weak version of it. So now try your own hand at proving by induction, and if necessary rewind the video and review the steps from Gauss' summation formula and try to transfer them to this problem. Here I want you to show that the sum of the first n odd numbers, so the sum from 1 up to 2n minus 1, is equal to n squared for all n greater equal 1. Okay, so we add only the odd numbers, 1 plus 3 plus 5 plus 7 and so on. And carefully state your initial case, induction hypothesis and induction steps so you can be sure not to make a mistake. Okay, I hope you gave it a try. The initial case n0 equal to 1, well, we have 1 is equal to 1 squared. Yeah, if we plug in 1 here, we get 2 minus 1, then we get 1 on the left hand side, and n squared 1 to the power of 2 is again 1, so not much to do for the initial case. We formulate the induction hypothesis. The reminder again, there's nothing to prove here, we just formulate that the desired statement should be true for a certain n greater or equal our initial value 1. That means we assume now that the sum from 1 to 2n minus 1 over all the odd numbers equals n squared. And now we do the induction step. We go from n to n plus 1. We consider n plus 1 squared and use the induction hypothesis. So we first expand this term here, n plus 1 squared is n squared plus 2n plus 1. And now here the n squared appears, and we can substitute this bit here by the induction hypothesis. So I mark this by IH here, so we make this substitution. 1 plus 3 plus 5, 2n minus 1 plus 2n plus 1. Yeah, and we can rewrite this a little bit as 2 parentheses n plus 1 minus 1, and then we have exactly this form here, but with n replaced by n plus 1. So the claim holds for n plus 1 as well. And now by the principle of induction we know that the equality here holds for all n greater our initial value 1. And now a few words of warning are in order. I must stress that it is absolutely necessary to prove both initial case and the induction step. Otherwise, proofs by inductions can go horribly wrong. And recall, in the induction hypothesis you don't have anything to prove. It's just an assumption you have to formulate to use in the induction step. Okay, let's look at some of these occasions where things go horribly wrong. Now I wish to prove that 5 to the power of n is strictly greater than 5 to the power of n plus 1 for all n greater or equal to 1. And I prove this as follows. My induction hypothesis is that the claim holds for a certain number n. And I can do the induction step. I look at 5 to the power of n plus 1, which I can write as 5 times 5 to the power of n. And now for this one I can use the induction hypothesis to show that this is strictly greater than 5 times 5 to the power of n plus 1, which again is 5 to the power of n plus 2. So my induction step actually works using my induction hypothesis. However, this proof is of course nonsense. 5 to the power of n is not strictly greater than 5 to the power of n plus 1 because, well, we didn't prove the initial case. So this is basically saying your dominoes are close enough that if one of them falls, they will topple all over, but the initial domino was never tossed over, so nothing will happen here. The initial case is missing, so this cannot work. Now we have an example where we won't do the induction step. So this means essentially we convince ourselves of the truth of a statement by checking one or more initial cases are true and assuming it will go on forever. Some mean people call this physicists' induction, but we are not mean people, so we shall never say something like that. And our claim is the following, that the expression n squared plus n plus 41 is a prime number for all natural numbers n. Well, let's check this. It works for 0, we get 41, this is prime. For 1 we get 43, it's prime. 2 we get 47, is prime. 3, 53 is prime. Oh, this looks good. 4, 5, they're all prime numbers. Up to 39, and I bet you wouldn't even have checked that far. So it's very easy to believe that, in fact, this expression is always a prime number. However, once we get to n equal to 40, we have 40 squared plus 40 plus 41, which is actually 41 squared. So this is not a prime number, because it's a square of a prime number, so it has more than just two divisors. And yeah, here we see that leaving out the induction step is wrong. And finally, I have another bogus induction proof for you, but here I leave it up to you to find the mistake. I make the claim that all horses have the same color, and I want to prove this by induction. So, first I do the initial case for n equal to 1. Well, here I'm just looking at one single horse, and obviously that horse must have the same color as itself. The induction hypothesis is now formulated as follows. For a certain number n greater or equal to my initial case 1, it holds that in every set containing n horses, all horses have the same color. The induction step is now as follows. I'm considering a set of n plus 1 horses, so I enumerate them h1 to hn plus 1. These are my horses. And then I look at two subsets, h1 to hn and h2 to hn plus 1. So these are two sets containing n horses each, so that in each of these two sets all horses have the same color. But due to the overlap, which is h2 to hn of these two sets here, all horses in the union of these two sets, which is our original sets of n plus 1 horses, must have the same color. But this just means our original n plus 1 horses h1 to hn plus 1 have the same color, and by the principle of induction it follows that all horses have the same color. Now, if you found the mistake, feel free to write it in the comments to this video. Please remember to like and subscribe, and thank you very much for watching.